Okay, we're going to be looking at higher order derivatives here, and notice they say find the second derivative. So what we have to do is first find the first derivative and then take the derivative one more time. So you can actually take derivatives, some of them like polynomials, you get to a point where you can't take the derivative anymore. You're going to be left with zero eventually. But some, like a sine and a cosine, those right there, infinite amount of derivatives. I mean, you'll never end. You'll never stop. You can continue to find successive rates of change. So for these examples here, at least for the first one, we're going to see that we're going to reduce it down considerably. We'll be able to take maybe, well, we'll talk about it. Let's dive in. Y prime, the first derivative, which is what we're not looking for. We're looking for the second, but we got to find the first, is 5 times 3, or 3 times 5, 15x to the second power, 3 minus 1, minus 2 times 6, which is 12x, and then we subtract 1 from the power, that's the first power, and then the derivative of 4 is just 0. So now we have y prime. Now let's find y double prime, okay, the second derivative. What does that look like? Well, that's 2 times 15, which is 30x, and then the derivative of negative 12x. Well, this x has a power 1 attached to it. 1 times 12, that's 12, so negative 12, and 1 minus 1 is 0, so we can actually just drop the x. All right, so we just drop the x. Anytime you have something linear, like this one right here, whatever's in front is its derivative, okay? So we have there the second derivative, 30x minus 12. All right, now clearly if we were to take the third derivative, we'd be left with 30. So let's just write that, y triple prime. You're just left with 30 because that basically is that linear portion, the slope, if you will, of the linear equation there, or the linear function. And if I were to find y quadruple prime, sometimes they might say something like this. All right, y with the 4 up at the top, that would be 0 because the derivative of that constant is 0. So we wouldn't actually be able to take the fifth, the sixth derivative because of the fact that it's just 0 at that point. But the same is not true on number 4. So let's take a look at number 4. If I have w equals z to the minus 3 minus 1 over z, first I have to rethink this. So z to the minus 3 is okay. It's this that I have to bring up with the negative exponent rule. So minus z to the negative 1. Looks something like that. All right, now let's find w prime. Okay, so we're going to bring down that negative 3 in the front, negative 3z, and then we're going to subtract 1. All right, and minus 3 minus 1 is negative 4. And then we bring down that negative 1 in front, we multiply, it's going to become positive z, and then negative 1 minus 1, negative 2. All right, we're still not done, so don't write it with positive exponents yet, because we need to find the second derivative. We multiply that negative 4 down by negative 3, we get a positive 12z, all right, minus 1, negative 4 minus 1, negative 5, and then the negative 2 gets multiplied down. So we have a negative 2z, and then subtract 1, that's negative 3. So that right there is our second derivative. If you wanted to express it using positive exponents, you certainly could. 12 over z to the fifth minus 2 over z to the third. And that's what it would look like, something like that. So either one is acceptable. Just be sure if you're like doing some kind of online homework system, you read the instructions, because it may say express using only positive exponents. So something to consider. So think about it. Okay. That's pretty much it. I mean, for finding second derivative, I mean, it could certainly get more complicated. But if you've got the power rules down, I think you'd be okay with this. So I hope this was helpful, and as always, like and subscribe.